Hello everyone, welcome back to the podcast. I'm your host, ichino-ani, and I am so excited to be here with you today. Today is Monday, March 2nd, 2026. You hope you are all having a wonderful start to your week. Today, we're going to look at a trending article from the Machine Learning Archive, and it is a really important one. The title is Model Agreement via Anchoring. The cron is arXiv. arXiv 2361. It is a bit of a long paper, but do not worry at all. I am going to break it down for you, just like we do in our classroom. So have you ever noticed how sometimes, even when two people study the exact same textbook, they might give completely different answers on a test? Well, artificial intelligence models do the exact same thing. This paper tries to solve a huge problem in machine learning called model disagreement, or predictive multiplicity. Let me explain what that actually means. Imagine we train two different machine learning models using the exact same kind of data, without letting them talk to each other. Because the training process involves a lot of randomness, these two models might end up disagreeing a lot when we ask them to make predictions on new data. In a machine learning world, this disagreement can cause a lot of headaches, especially in real-life situations. The researchers in this paper wanted to figure out a way to guarantee that these models will naturally agree with each other right out of the box. And they wanted to do this without changing the standard ways we train models today. Their solution is something they call the Midpoint Anchoring Method. Instead of forcing two models to be exactly the same inside, they use a clever thought experiment. They imagine a hypothetical model that is the exact average, by the midpoint, of the two independently trained models. Then, they use some very smart math to show that if both models are doing a good job at minimizing their errors, they must be very close to this midpoint. And if they are both close to the midpoint, they must be close to each other. It is like if two students are both standing very close to the teacher, they have to be standing close to each other, right? This is so cool because it works for non-convex model classes, which are usually very messy and unpredictable. Let me explain the math just a little bit more because it is quite elegant. The core of their technique uses a mathematical identity for squared loss, which breaks down the error of an average model. Normally, researchers use this rule to measure the error of a combined ensemble model. It shows that the error of the average model is equal to the average error of the individual models, minus a term that measures how much the models disagree with the average. The authors of this paper flipped this equation completely around. They used it to measure the disagreement itself, by nicking up between the individual errors and the average error. This simple but powerful trick is what unlocks the amazing results. Now let us delve deeply into how this actually applies to everyday life, because I promised you 3 specific application examples. First, think about medical diagnosis at a massive hospital. Let us say doctors use an AI system to predict the risk of a patient developing a certain serious disease. And hospitals frequently update and train these AI systems with new patient data to keep them as accurate as possible. If the new model suddenly disagrees with the old model and gives a completely different risk score for the exact same patient, the doctor might lose trust in the AI entirely. This is called model churn. And it is very confusing for medical professionals who rely on stable advice. By using the concepts from this paper, hospital systems can guarantee that the newly trained model will largely agree with the old one, providing stable and trustworthy care for patients. Second, let us talk about fairness in things like bank loans. Imagine 2 different banks use the same type of data to train their own independent AI models for approving financial loans. If the training process is highly random, one bank might approve your loan, while the other bank denies it, even though they're learning from the exact same data patterns. This feels very arbitrary and incredibly unfair to the person applying for the loan. If banks apply this anchoring technique, they can ensure that independent models will reach an agreement on most inputs. This means your loan decision will not just depend on the random luck of how the AI was trained that day, making the whole financial system much fairer for everyone. Third, consider complex systems like self-driving cars on busy city streets. A self-driving car uses many different machine learning models connected together in a long pipeline. One model might detect pedestrians walking on a sidewalk, and it sends that crucial information to another model that controls the physical brakes. If the pedestrian detection model is retrained and suddenly changes how it makes predictions, even if it is still technically accurate, it can break the braking model that relies on its specific behavior. The stability guaranteed by this paper means engineers can safely update individual parts of the self-driving car without causing the whole system to fail. Right. So, how does this compare to other technologies out there? There are other ways people try to make models agree in the industry. Some researchers use test-time interaction, where two models basically talk to each other and vote on the best answer before deciding. But that takes extra time and extra computer power right when you actually need the prediction the most. Other researchers use something called strict replicability, which forces the training algorithms to be perfectly identical every single time. But strict replicability requires using very slow, custom-designed algorithms that are simply not practical for big real-world problems. What makes this paper so amazing is that their anchoring method works on existing, popular machine learning algorithms that people already use. They mathematically proved it works for 4 major techniques. First, they looked at stacked aggregation, where you train many base models and combine their answers. They showed that as you increase the number of base models you stack, the disagreement naturally drops to 0. Second, they applied it to gradient boosting, which is a super popular method used for tabular data, like big spreadsheets. It proved that the disagreement goes down as you increase the number of boosting iterations. Third, they investigated neural networks, which are the powerful systems behind modern AI breakthroughs. They found that by anchoring to a midpoint network that is twice the size, the disagreement shrinks as the network gets larger. And fourth, they proved it works for regression trees, showing that deeper trees led to more agreement between independent runs. Let us look closer at the neural networks and regression trees, because this part is absolutely fascinating. These models are notoriously non-convex, which means their internal mathematical landscapes are full of hidden hills and deep valleys. If you train 2 neural networks independently, the internal weights and structures might look absolutely nothing alike. They could end up in completely different valleys in that mathematical landscape. But the authors realized that the average of 2 neural networks of a certain size can always be represented by a single neural network that is exactly twice as big. Because of this clever insight, they can anchor both networks to this larger, combined network. They discovered that as long as the learning curve is relatively flat, meaning that doubling the size of the network does not drastically reduce the error, the 2 independent networks must make very similar predictions. This is incredible because it proves that even if the insides of the AI models are totally different, their output behavior are perfectly consistent. They linked all of this to something called the local learning curve. Basically, if making your model a little bit bigger does not massively improve its accuracy, it means your model is in a highly stable state. And this paper proves mathematically that this stable state also guarantees that independent models would agree with each other on their final answers. It is truly a brilliant way to look at the geometry of machine learning predictions. Instead of looking at the complex, messy parameters inside the models, we just look at the final predictions, which is what we actually care about in the real world. Furthermore, they generalized their findings beyond simple squared errors. They showed that their anchoring method works for any multi-dimensional strongly convex loss function. And for gradient boosting, they even introduced a variant using the Frank-Wolf optimization algorithm. By restricting the models to a specific mathematical budget, they proved that you can completely control the trade-off between how accurate the models are and how much they agree with each other. This gives engineers a practical knob they can turn to guarantee it is like finding a universal rule for how students learn, no matter what subject they are studying in school. By ensuring that our AI systems are stable and consistent, we can build a future where humans and machines work together smoothly, without any sudden surprises. Well, that is all the time we have for today, my dear listeners. I hope you enjoyed this deep dive into the fascinating lore of the machine learning agreement. Keep asking big questions, keep learning new things, and I will see you all next time.